Swayam Prabha. Digital India. Educated India.
Welcome to Module F, Lecture 3. In this lecture, we shall continue our discussion about car following theory. In Lecture 2, I explained to you various models, first generation, second generation, third generation, fourth generation and fifth generation models. All these models which were developed by General Motors. I explained to you fifth generation model is the most generalized model, and all the other four models are special cases of the generalized fifth generation model. While I explained to you the basic idea or the concept and the model form, I said that we will continue our discussion with an example problem. So, that is what we are going to do now. So, let us take an example problem. The leading vehicle and following vehicles are travelling with a speed of 15 meter per second. So, both are travelling at the same speed and with a space headway of 20 meter. So, initial speeds both vehicles are same, spacing or space headway is 20 meter. Then at time t equal to 2 seconds, the lead vehicle accelerates by 1.5 meter per second square for 2 seconds and then further decelerates by 1 meter per second square for the next 2 seconds. With this background, what we want to simulate the behavior. Behavior means the response in terms of acceleration, speed, also the position of the following vehicle for every 0.5 second interval. So, every 0.5 second interval we want to update. So, you can call it also a scan interval. Using General Motors car following model where L is 1, M is 0, you know already what is L, what is M, and the sensitivity coefficients alpha Lm equal to 12, the reaction time is 1 second. So, this is reaction time, that is 1 second, and we want the update at 0.5 seconds interval, that is the scan interval. So, how to calculate it? Before we show you the calculation, before I explain you the steps, let us look at the generalized model, car following model as proposed by General Motors. This is the fifth generation model. So, this model form is known to you. The response in terms of acceleration, deceleration at time t plus delta t depends on the alpha, a constant which is already given. This is the speed of the following vehicle at time t plus delta t, but since m equal to 0, this term will get omitted. Then divided by x n t minus x n plus 1 t. So, it is the distance headway between space headway between vehicle n and n plus 1 to the power L, L is taken as 1. So, m is 0, L is 1. So, it actually indicates that this is the third generation model as proposed by General Motors, multiplied by relative speed of two vehicles. So, x dot n at time t minus x dot n plus 1 at time t. Now, remember that time t what is happening, that the response we are trying to model after time delta t, which is the reaction time. This is very important. So, the simplified form of this generalized model as per the third generation model, given coefficient indicates, giving values indicate that it is actually a third generation model. So, I have written it. Now, using this model, we shall calculate all the values which are asked in the example problems or question, that what will be the acceleration, what will be the speed, what will be the position of the following vehicle at scan interval of 0.5 seconds. Here I have shown the calculation for the first 3.5 seconds, 3.5 seconds, simply because otherwise it will be too lengthy. So, I wanted to show it only for 3.5 seconds and explain you the calculation, then I will show you the entire calculation. Let us go column wise. We want the scan interval of 0.5 seconds. So, start with 0 and 0, 0.5, 1, 1.5, 2, 2.5, 3 and 3.5. Like that it will go for 15 minutes, because that is what we eventually want, okay, or for even longer time, right. Now, so that is understood. X double dot 1 leading vehicle acceleration. So, we know at time t equal to 0, it is 0 for the first 4 interval, time t 0.5, 1, 1.5. At 2 seconds it starts doing the acceleration. So, at 2 seconds the value will be 1 for the next 2 seconds. So, that means 1.2, 2.5, 3 and 3.5 all will be actually 1.5 seconds. Look at this problem carefully. At t equal to student lead vehicle starts accelerating at 1.5 meter per second square for 2 seconds. So, when it is exactly t equal to 2, acceleration starts. So, at that time, so at t equal to 2, we have taken the acceleration. So, these are basically inputs. So, similarly, in subsequent time also when I show you the full table, you will see this is given input. So, first column is given input, second column is again given input, third column is the speed. Now, this can be calculated. Initially, we said that it is travelling at 15 meter per second, both the leading vehicle and the following vehicle. So, now we are doing the leading vehicle calculation, and leading vehicle we know it starts accelerating from t equal to 2 second onwards. So, at t equal to 2 second also it will be 15 meter per second speed, because that is the time when it starts accelerating. So, how to calculate the remaining values? I am showing you one calculation. Suppose at t equal to 2.5, how we can get the x 1 dot leading vehicle speed. So, the cell which we are going to calculate, I have indicated it in green. We are going to use a simple formula which you all know, V equal to u plus a t. So, here we are talking at t equal to 2.5 seconds, what is going to happen? So, when you are talking about trying to calculate the value at t equal to 2.5 seconds at 0.5 second scan interval, as I have indicated here that as capital T. So, that means our u is at 2 seconds. So, what is the initial speed at t equal to 2 seconds, 15 meter per second is given. What is the acceleration at t equal to 2 second, 1.5 meter per second square, and what is my this interval t, capital T, it is nothing but the scan interval, always it will be 0.5, but this is the time gap here between 2.5 seconds and 2 seconds, that 0.5 seconds. That is why I have shown the calculation here. The remaining is simple. So, V equal to u plus a t, you put the u value as 15 meter per second, a as 1.5 meter per second square, and capital T equal to 0.5 seconds or 2.5 minus 2. So, you get 15.75. So, this cell you get. And now, using the same approach, you can calculate all the remaining cells in the same column. So, column 1 input, column 2 is also direct input, column 3 we know how to calculate, right. Now, next go to column 4. So, in this slide I am going to explain you how you can calculate a cell in column 4. Here I am going to again explain you that at t equal to 2.5 seconds, how we are going to calculate the value of x 1, all leading vehicle till now. So, leading vehicle acceleration is known, we calculated leading vehicle, then the speed, and we want to calculate the x 1, the distance, right, from the reference point. So, how we can calculate the distance? So, this was like initially as it is said that initially it is said that the space headway is 20 meter. So, we are considering the x 1 at t equal to 0 is 20 meter. Then we are going to use again a simple formula, s equal to u t plus half of a t square, a is the acceleration. Now, in all these calculation, initial calculation, the a is 0, because you can see the x dot values as 0, and therefore, wherever a will be other than 0, this half a t square also will come. Let us take the generalized s equal to u t plus a t square and try to see how we can calculate the x 1 value at t equal to 2.5 seconds. So, when we are talking at trying to calculate the distance at t equal to 2.5 seconds, we are trying to calculate how much distance it will move in between 2 and 2.5 seconds. So, within that 0.5 seconds, how much distance it will move. So, what is the u? U will be taken as speed at time t equal to 2, that is 15 seconds, 15 meter per seconds. A is again at time t equal to 2, what is the acceleration? 1.5 meter per second square, and what is the t value is the difference between 2.5 and 2 scan interval. So, that is 0.5. So, s equal to u t plus half a t square, a value is known, u is known, capital T is known. So, you get the s as 7.69. Then what will be the distance x 1? It will be at 2 seconds it was 50. So, in between 2 and 2.5 seconds, at 2.5 it has travelled another 7.69 meter. So, the total is 50 plus 7.69, 57.69. So, you know how to calculate the cell. So, once you know this, you can calculate all the cells in column x 1. So, we are through with cell 1 input, cell 2 as input, cell 3 calculation, cell 4 calculation. Now, we go to cell 5. Here we are actually trying to calculate the response, acceleration, deceleration, whatever it is, right. Obviously, you know, you put to this formula, you know, when both vehicles are travelling at the same speed, obviously for the first 0 at 0.5 at 1 and at 1.5, even at 2 also the you know the deceleration whatever will happen, let us that we can also calculate, but the initially it will be all 0, right. The response will acceleration, deceleration, the response will be there once the vehicle in front, the leading vehicle start accelerating or decelerating. So, let us try to see how we can calculate a cell. Let us take the cell corresponding to time t equal to 3.5 seconds. Now, this is the cell, the green one that we are going to calculate. So, what will be the acceleration or deceleration of the following vehicle at time t equal to 3.5 seconds. But as you know, if we are trying to calculate the cell, it is actually in this equation t plus delta t, that is the t here, because we are taking the time clock. So, at 3.5 seconds what is going to happen, that is the response is happening after 1 second, because that is what the reaction time. So, delta t is 1 second. So, we will take the values like the speed at 2.5 seconds, because the reaction time is 1 second. So, x 1 dot at 2.5 we will take, we know that it is 15.75, x 2 dot at 2.5 it is, we know that it is 0, it is 15 meter per second. Then x 1 2.5, this is 57.69, x 2 2.5, the following vehicle, it is 37.50. Then we go to this equation, third generation General Motor model. We know it is 12 by x n t minus x n plus 1 t. So, this will be simply x 1 and x 2 you can consider. So, the x 1 values are known, also the x dot n and x dot n plus 1, all we are taking at time t 2.5 second. What is the value? That is the basis for calculating the response after delta t time, the reaction time. So, t plus delta t is the time clock. So, you calculate it as 0.45 meter per second square. So, exactly in the same way, now you can calculate all the cells in this column x 2 dot. That means, the response of the following vehicle. So, next it will be x 2 dot and x 2. So, we are going to explain you now how you can calculate x 2 dot and x 2. Let us take that both we are trying to calculate at 3.5. Again the basic equation is v equal to u plus a t, simply you can get this value, right. So, at 3.5 means 0.5 second interval, that is the scan interval. So, we will take the u value and a value at t equal to 3 seconds, and obviously, delta t again capital T is again 0.5 second, that is the scan interval. So, you can get v, you can get s, you can get using this formula u t equal to half of the t square. So, once you get this s, so what will be then 45 plus s, and once you get the speed, that is going to be used for the calculation of the other values. So, that way the whole calculation is explained. Now, what is remaining is really x 1 dot minus x 2 dot and x 1 minus x 2. That is very simple, because if we know x 1 dot also we know, x 2 dot also we will know the speed of lead vehicle and following vehicle at any time t. So, we can find out what is the relative speed. We also know x 1, we also know x 2. So, we can calculate at any time interval t what is going to be the value of x 1 minus x 2. I have shown it here for time t equal to 3.5 seconds. So, you can see that. So, that way all the cells, now you are through with all the columns. So, 1 is input, 2 is input, 3 onwards 3, 4, 5, 6, 7, 8, 9. All these columns how we calculate I explained. So, here I am showing the complete table for the first 15 seconds, not shown the complete table really. The initially I have shown here up to 8 seconds, and then the last 14.5 and 15 seconds you can even calculate and try to match. What is important for you to note that at 2 seconds it starts accelerating. So, the x 1 dot value at 2 seconds is taken as 1.5, and then it is said after 2 seconds it start decelerating. So, again at 4 seconds onwards the value is taken as minus 1. So, not that at 2 seconds also it will be 0, because at 2 seconds only it starts accelerating at 2 seconds. So, at 2 seconds it starts accelerating. So, the value is 1.5, not 0. So, similarly after 2 seconds means at 4 seconds we will start taking the minus 1. The remaining all calculation I have explained. Now, here I am trying to show how the curve will look like. X axis is the time, y axis is the acceleration. So, the black line shows the leading vehicle, how the acceleration is value is changing over time, and the red one shows for the following vehicle, which we tried to model using the car following model actually. We tried to capture using car following model. So, you can see that, and it is so interesting to see that we are actually able to model the response in terms of acceleration or deceleration, because here in this segment it is acceleration and in this segment it is deceleration, right. So, how the response is happening, and always the following vehicle lags behind the lead vehicle. So, it start doing the acceleration, then it also start doing after a lag, right, and it again decelerates. So, it also start reducing and finally, it decelerates also after some gap. So, it is trying to catch up, right. Here it is shown the speed profile of leading and following vehicle. You can also see the speed is increasing, here also after some time it is increasing, it is reducing, this also is, then the following vehicle is also reducing the speed, but it is not just a shift in time, but the overall pattern and the values are also very different, right. So, the pattern here is the black line pattern and the red line pattern is different. Here also the pattern for the variation for the red black line and the pattern what is shown as the red line, they are not same, not just a lateral shift, but the values are also different, but suddenly it is going to respond, right. So, if the lead vehicle is accelerating, the followed vehicle is also trying to accelerate, but not exactly in the same way, right. There is of course a gap, and but also not exactly in the same manner. Here we are trying to show the relative speed, and here it is the distance headway, very interesting distance headway. The relative speed also shows that it is always trying to catch up, right. So, relative speed is suddenly the front vehicle or lead vehicle accelerates. So, the speed relative speed becomes higher, but then immediately in the response the following vehicle also start doing the acceleration, so that it can catch up. So, it is always trying to catch up, okay, trying to catch up, and the relative speed almost tending with some oscillation, it is trying to keep the relative speed 0, trying to do that, right. But there is pattern is different, lag is different, there will be a time lag also in the response. The nature of response is also not exactly the way the lead vehicle behave, the following vehicle will behave exactly in the same manner, not like that. You are seeing that everywhere. So, this is what it is, and the distance headway figure is most critical, what I have shown here, since it indicates whether a minimum safe distance headway is maintained at one end and the reasonable capacity in a larger context, right, overall context, a reasonable capacity is obtained on the other hand. So, the distance headway, that is why it is very critical, because it influences the safety, it will tell you that whether the response is going to be safe. It is that safety is very important, because it depends on the space headway, and also finally the capacity also depends on the headway, or inverse of headway is 1 by headway is actually the distance headway is actually the density. So, density influence the throughput, right. The capacity also will depend on that, and all traffic parameters, it is going to be influenced by this behavior. So, the space headway or the distance headway is very, very important, and we are able to get that, right. We are able to model that. So, with this, now let us go to another topic. It is the General Motors model, which is a microscopic model, and the macroscopic traffic model, what you have studied earlier, Greenshell's model, Greenberg's model, and so on. Is there any relation? Can they be linked? That is the part we are going to discuss now. So, what happened? Port of New York researchers developed macroscopic model of speed, Greenberg's model. You can see mu equal to mu 0 into ln kj by k. Mu is the specimen speed, obviously k is the density, mu is here the optimum speed, that is the speed at capacity, and kj is the jam density. Now, optimum speed, as I have said, it is the speed when existed when the traffic flow level is at capacity. Now, interestingly, rather very interestingly, researcher found that numerical value of alpha 0 in the third generation model, you know this term alpha 0 in the third generation model, and the value of mu 0 here, the Greenberg's model, this is Greenberg's model mu 0, they were almost identical for different highway facilities. The data came and they found what is the value of mu 0 in Greenberg's model, and then in General Motors third generation model what is alpha 0. These values were almost identical for different highway facilities. Then they started thinking, is it just a sheer coincidence or really they are same? What is the mu 0 here in Greenberg's model and what is alpha 0 in the third generation microscopic model proposed by General Motors? Are they the same thing? Because one is macroscopic, one is microscopic. So, they started doing the researchers started working further investigations, and eventually they found a connection that I am going to explain you how they got. So, let us take the third generation microscopic model, remember it is microscopic model and whereas Greenberg is macroscopic. So, can we get from this model, can we really get this third generation General Motors model, can we get the Greenberg's model? That was the attempt. So, what if you integrate this with respect to t under steady state condition, then it is x double dot acceleration. So, you get speed x dot n plus 1 alpha 0 and this whole term obviously becomes log of ln x 1 x n minus x n plus 1, because here in the denominator it was x n. I have omitted the t term here, right, because for simplicity. So, x n minus x n plus 1. So, it comes ln of log of this plus a constant term. Now, if mu is the specimen speed in Greenberg's model is substituted for this x dot n plus 1. What is x dot n plus 1? It is speed. So, if we consider that is the specimen speed, that is the way the whole traffic stream is behaving under steady state condition. So, this x dot n plus 1 can be replaced by mu, quite possible, and also what is x n minus x n minus 1? It is the distance headway, spacing or space headway. So, 1 by that is what? Density, macroscopic parameter density. So, we do that x dot n plus 1 replacing by mu, and this x n minus x n minus 1 we are replacing by 1 by k, because 1 by distance headway is the density plus C 1. We have moved one step, one small step we have proceeded. still it does not look, yes, 1 by k has come, but plus C 1. So, now let us see what we can do with the C 1. C 1 also can be written, it is a constant, it can be written as alpha 0 into ln C 2. So, what was C 1 a constant, we can substitute that and we can write it like another constant alpha 0. Here also alpha 0 is there. So, we write alpha 0 and ln C 2. Always we can write, because after all it is a constant. So, what you get here? Mu equal to alpha 0 into ln C 2 by k. The form has come, already it has come. It has already come. It now looks like something like a Greenberg model. Of course, there is still we do not know what is C 2, where alpha 0 is there, whether how we can know that that is really mu 0, that we do not know, because our this form is mu 0, but this overall looks has come, these look very similar. Mu equal to alpha 0 into ln C 2 by k. Now, our next step was to understand what is then C 2, how we can get the value of C 2, because here it is actually k j by k. Is that C 2 is equal to k j? What they did, okay, let us take when k equal to k j at jam density, then obviously mu equal to 0, speed is 0. So, you take speed is 0, k equal to k j, then alpha 0 into ln C 2 by k. Now, this what it tells you? This is 0, alpha 0 is again a constant. So, obviously, it indicates that C 2 is actually k j. So, we got it, mu equal to alpha 0 into ln k j by k. Mu equal to mu 0 into ln k j by k. The only difference is here is mu 0 and here it is alpha 0. Even by comparing these two also you can now say this must be mu 0 and alpha 0 must be same. We got the other form, but now still let us see if we can even bring with little bit of more analysis, if we can bring alpha 0 as mu 0. What was done? You know, q equal to u k, flow equal to speed into density at macroscopic level, speed flow density are related. So, let us multiply both sides by k. So, k into mu speed flow and here k into alpha 0 ln k j by k, same alpha 0 only we have taken the k, multiplied it by k both sides. Now, if we differentiate this flow with respect to q, why? That is where the capacity, right. So, at capacity we know k equal to k 0, optimum density. When the dq dk equal to 0, then whatever is the k value, that is the optimum density, density at capacity. So, dq dk you take, do the derivative, make it 0, and when you make it 0 and already we have taken know that k equal to k 0 in that case. So, if you solve, you get actually k 0 equal to k j by E, fine. Now, go back to this equation 9.15, mu equal to alpha 0 into ln k j by k. Substitute mu equal to mu 0 and k 0, because that is the capacity point that we are trying to understand. What happens then this equation? So, mu equal to mu 0 and k 0 we are replacing by k j by E. What we get here? We get here then mu 0 equal to alpha 0 ln k j by Kj by E. That means mu 0 equal to alpha 0 actually. So, now you simply substitute in equation 9.15 what was there mu equal to alpha 0 ln Kj by K, but since alpha 0 equal to mu 0. So, you substitute that, make it mu 0, what you got? You eventually got Greenberg's macroscopic model. So, we started with third generation microscopic model as proposed by General Motors, and with some simple steps and substitutions, we could derive this Greenberg macroscopic model. Strong tie, and this is really amazing and very important discovery, because looking at the traffic step, you look at the microscopic with help of microscopic parameter, look at with the help of macroscopic parameter, there is a connection. So, that was established. In fact, the generalized GM model, which can be written as I have shown it in terms of L and M, actually I will stop here with this closing kind of statement. Actually, you can see and you can get with what value of L and M you are taking, then it is possible that the GM model generalized model with specific different values of L and M can actually give you several microscopic model. As I have shown you, for some combination third generation model specifically, it gives you Greenberg model when L equal to 1, M equal to 0. Similarly, with some other combination of N L M, you can also get with M as 0 and L as 2, you can get actually the Green-Schultz model. Another combination can give you underwood model. So, that shows the strength of the generalized model, fifth generation generalized model as developed by General Motors, that with different L and M you can actually get several models, established models, which have been developed independently by researchers and which are all macroscopic models. So, there is a strong connection. So, what we discussed? We discussed the General Motors theory in the previous lecture. We took an example problem to explain that, and then also the other part, the connection between generalized Motors model, the generalized fifth generation model, GM model, because all other models are specific cases of the generalized model, fifth generation model. First, second, third, fourth generation, all are some specific cases of the fifth generation model. So, generalized GM model, General Motors model, and the connection between that and the macroscopic traffic flow model. I explained only Greenberg, but you can get Green-Schultz, you can also get other models from that, right. So, thank you so much.